Okay, Ohanian 11.31 from homework number 10 has a couple of balls hanging from strings of length L. This one has a mass 2m, and you have another one that's hung so that whenever it would hang straight down, it would hit. But in fact, it's pulled off initially to the side. Oh, by the way, this one has a mass m. It's initially pulled off to the side, so its center of mass is a height h above its center of mass at the low point. Okay, so you pull this one up to that height, release it, it's going to swing down, it's going to strike this ball. You're told to assume the collision is elastic, and then in part A you're asked, how high will each ball swing after the collision? Well, this is sort of like one of the examples I gave you in the lecture notes where you have to analyze the collision separately from motion before or after. During the collision, you've got conservation of momentum always to work with. And in this case, since it's elastic, you also have conservation of energy. But before the collision, to get the velocity that this mass has just before the collision, you have to do that separately. But in this case, it's not too bad because we can use conservation of energy. If it drops by a height h, then the potential energy of gravity gets translated into the potential energy of the motion. So part A, we'll use conservation of energy to say that the initial energy equals the final energy. The initial energy is all gravity, assuming you define potential energy of gravity as 0 at the low point. That equals the final energy. When I say final, I mean just before this first collision. So 1/2 mv squared. And so we have that expression, v equals the square root of 2gh. Okay, now that's in general for anything that falls by a height h under the influence of gravity near the Earth's surface. And so I'll just call that v1 naught. The original velocity of v1, we'll call this mass 1, this mass 2. v1 naught is just equal to the square root of 2gh. Okay. Now what we're after is after the collision. Now we can't go from this velocity to how high up they each bounce. We have to analyze the collision separately and then worry about how high up they bounce. So we have to find the final velocities. Question, what's v1 final and v2 final after the collision, but before they start rotating back up again to some heights h. And how are we going to do that? Well, you could start from the basic principles of conservation laws of momentum and energy. That's how you might be asked to do it on a test. In this case, I've already done the work, and I showed it to you in lecture. This is the expression for the velocities after a collision, okay, in terms of the masses after an elastic collision, and the initial velocities. So I'm going to go ahead and use my earlier work to just write down the answer. Okay, so v1 final equals m1 minus m2. Okay, but that's just, well, actually, let me start with the v1 naught, which is the square root of 2gh. That's this term times m1 minus m2, but m1 is m and m2 is 2m, so that's just a minus m divided by m1 plus m2, and that's just 3m. Okay, and v2 naught, remember, is 0, so this term goes away in both expressions. So I have minus 1/3. The square root of 2gh is the velocity of this block after the collision. Notice it's negative, so it's going to be bouncing back up to the left. How about v2 final? Okay, well, that's this expression, and again this term is 0, so I just write v2 final equals v1 naught square root of 2gh, and here we have 2m1, which is just 2m divided by m1 plus m2, or 3m, so that's plus 2/3 square root of 2gh. So that tells me after the collision, this ball block bounces back with 1/3 of its initial speed, and this one goes in this direction with 2/3 of the initial speed that m1 had. Okay, and now we're ready to find the heights after the collision. And let me just call those h1 prime. How high up does the first ball head after the collision? And H2 prime after the first collision, so I use a single prime. Well, now that we have the velocities it each has after the collision, we can again go back to conservation of energy to say that 1/2 mv1 final squared, its kinetic energy, will all be translated into potential energy of its height after the collision, h1 height. I can solve this for h1 prime. That's equal to v1 final squared divided by 2g because the m's cancel. Okay, but you shouldn't give formula in terms of intermediate quantities like v1f that we calculated. Give it in terms of the things you were given. And we know v1 final is 1/3, -1/3 the square root of 2gh. If I square that -1/3, I'll get 1/9. Yeah, 2gh. Square root of 2gh squared is 2gh divided by 2g is 2g. And so I've got h over 9. The g's cancel, the 2's cancel. So the first ball will come down a height h and then bounce up back up 1/9 of the height h. The second one is going to result, the second change in height is the initial kinetic energy. Initial means after the collision, but before it starts rebounding up or bouncing upwards. V2 final squared equals m. Now, you could argue I should write 2m in here because this one has a mass of 2m. We'll see that doesn't matter, but maybe I'll go ahead and put it in anyway. 1/2 2m v2 final squared equals 2m gh2 prime. How high up does it go? Well, again, the m's cancel. I'm trying to solve for h2 prime, so the m's cancel. Didn't have to worry about those. The 2's cancel, so I didn't really have to worry about those. And it's equal to v2 final squared, okay, divided by 2g. Plug in our result for v2 final up here. So that's 4/9 times 2gh. 4/9 2gh divided by 2g. And I've got 4h over 9. So this ball will go up higher. It'll go up to 4/9 h. This one will only go up to 1/9 h after the first collision. Okay. So that's part A. Part B, I'll start with a fresh piece of paper because it's even more algebra. So part B says, okay, after they both bounce up to their respective heights, they're going to swing down and collide once more at the bottom. Okay, so after the second collision, how high up will they rebound? Well, we actually just follow the same techniques, but now let's redefine things. It's the second collision, but I can say the original velocity before the second collision for v1 is just 1/3 times the square root of 2gh. And the original velocity for the second one, just before the second collision, is minus 2/3 the square root of 2gh. And where these numbers came from was just earlier result. Okay, if they had these velocities right after the first collision, they transferred that to potential energy in terms of the height, but then this gets transferred back down into these same velocities again because energy is conserved. So just before the second collision, these are the velocities they have. And so now we can analyze the collision. It's another elastic collision, so I can go back to my expressions here. But things are a little bit harder. In the first collision, v2 was 0, but that's no longer the case. So I have just a slightly more complicated expression for each one of these. But I can still use this, these equations I derived. And I can say after the second collision, v1 final, well, it's going to be v1 naught, but v1 naught is equal to 1/3 the square root of 2gh, that's just this term, times m1 minus m2. Well, that's just divided by m1 plus m2. Well, that's just our -1/3 again. That's this expression. Plus v2 naught, plus v2 naught, well, v2, actually, I don't have the negative sign here. I should put that in because it's moving to the left. So plus v2 naught is actually minus 2/3 the square root of 2gh. Okay, and then I've got 2m2. Well, m2 is 2m itself, so that's 4m divided by 1 plus 2, or 4/3. Okay, so that's my expression. This is the math I have to do. Well, it's 1/3 times 1/3 is 1/9, negative 1/9 minus 8/9. Well, that's just 1. So this is equal to negative the square root of 2gh. And so that's the velocity of the first ball after the second collision. Now I can analyze, before I bother with the second ball, let's just go ahead and analyze how far up this one's going to bounce. I do that now after the collision using conservation of energy. Its height the second time up will be given the energy that it has, potential energy is mgh prime, will be equal to this 1/2 m v1 final prime squared. Okay, and so solving for h1 double prime, this second height, the m's cancel. So this is just v1 final squared divided by g. But v1 final is our square root of negative square root of 2gh. Okay, and so squaring that, I just get 2gh divided by, sorry, this was 2g here, forgot that factor of 2, divided by 2g. 2g's cancel. So lo and behold, it flies back up to its original height after the second bounce, which is going to look interesting in real life. Okay, so now let's go ahead and analyze what happens to the second ball, the 2m ball. And so we do the same thing. After the second collision, it's going to have a velocity, and here we're using this expression. It's going to be equal to v1 naught, and v1 naught was 1/3 the square root of 2gh from up here, okay, times 2m1 divided by m1 plus m2. Well, that's just 2 times little m, or 2 divided by 1 plus 2, or 2/3. Plus v2 naught, and v2 naught actually, I should write a plus because that was a negative 2/3 the square root of 2gh. Okay, and now I have 2m minus m, or just m divided by 3, or 1/3. Okay, and here we just look at this and we say, well, we've got 1/3 times 2/3, or 2/9, minus 2/9. That's just 0. Okay, so it leaves with, after the collision, it's left with 0 velocity, and conservation of energy obviously says mgh2 prime, or double prime, then it has to be equal to 0 because you've got no kinetic energy to start with. So h2 double prime equals 0. So the system starts pretty much like it exactly like it started, with the first ball up at a height h and the second ball stopped at the bottom. Okay, that's it.